In this video, we talk about the nth roots of complex numbers and some miscellaneous facts related to the nth roots of complex numbers. The first fact is a general formula for the nth root of a non-zero complex number. Then we take a look at the plot of the nth roots of 1 for n greater than or equal to 3. This segues nicely to the fact that if zeta is a non-real nth root of 1 so that zeta is not equal to 1, then 1 plus zeta squared plus etc., 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 all the way to zeta raised to the n minus 1 power equals 0. This leads to a pair of equations that say that for n greater than or equal to 2, the sum from k equals 0 to n minus 1 of cosine of 2 pi times k over n is 0, as is the sum from k equals 0 to n minus 1 of, this time, sine of 2 pi times k over n. If z is a non-zero complex number, then z equals its absolute value times e raised to the power I times theta, where theta is an argument of z. In general, z equals its absolute value times e raised to the power I times the quantity theta plus 2 pi times k, where k is an integer. Let n be a positive integer. We say that v is an nth root of z if and only if v to the nth power equals z. We'll refer to this quantity as the real number nth root of the absolute value of z. We'll call it plainly as the nth root of the absolute value of z. We have to make a distinction since even a non-zero real number like 1, for example, has n distinct nth roots. So from now on, when we say the nth root of the absolute value of z, we mean only the real number nth root of the absolute value of z. We set alpha equal to theta over n. Then the nth root of the absolute value of z times e raised to the power I times alpha, or the nth root of the absolute value of z times e raised to the power I times theta over n, is an nth root of z, since by raising this product to the nth power, we get the real number nth root of the absolute value of z raised to the nth power, giving us the absolute value of z times e raised to the power I times theta over n raised to the nth power, or e raised to the power I times theta. And the absolute value of z times e raised to the power I times theta is z. We leave it as an exercise for the viewer to verify that the absolute value of z times e raised to the power I times the quantity theta over n plus 2 pi times k over n is also an nth root of z for every integer k. Adding 2 pi times k over n to theta over n is a counterclockwise rotation around the origin by the angle 2 pi times k over n. And by adding 2 pi over n sequentially, we get the next root, then the next, and the next, etc., etc., etc. To generalize, a rotation clockwise or counterclockwise of an nth root of z by the angle 2 pi times k over n, where k is an integer, is also an nth root of z. The converse is also true, that if v and w are nth roots of z, then v and w are rotations of each other, clockwise or counterclockwise by an angle 2 pi times k over n for some integer k. In order to prove this converse, let an argument of v be beta and let an argument of w be delta, so that v equals its absolute value times e raised to the power I times beta, and w equals its absolute value times e raised to the power I times delta. Since v and w are nth roots of z, v to the nth power and w to the nth power are both equal to z. We divide everything by w to the nth power to get the absolute value of v to the nth power over the absolute value of w to the nth power. We also have e raised to the power I times the quantity beta minus delta times n, and this product should equal 1. Taking the absolute value of only the exponential, we maintain equality since the other factors are real and non-negative. e raised to the power I times the quantity beta minus delta times n is cosine of the quantity beta minus delta times n plus I times sine of the quantity beta minus delta times n, so that its absolute value is the square root of cosine squared plus sine squared, both of the quantity beta minus delta times n, and this gives us 1 for the absolute value. Therefore, the absolute value of v to the nth power over the absolute value of w to the nth power equals 1, so that the absolute value of v equals the absolute value of w, since these absolute values are both real and non-negative. One can actually show that the absolute values of v and w are both equal to the nth root of the absolute value of z. We also have e raised to the power I times the quantity beta minus delta times n equals 1, so that the quantity beta minus delta times n must be an integer multiple of 2 pi, so that the quantity beta minus delta times n equals 2 pi times j for some integer j, or that delta equals beta minus 2 pi times j over n. We replace j by minus k, so that delta equals beta plus 2 pi times k over n. Therefore, w equals its absolute value, which is equal to the absolute value of v, times e raised to the power I times the quantity beta plus 2 pi times k over n for some integer k, so that every nth root w of z is a counterclockwise rotation of another nth root v by the angle 2 pi times k over n. Let n be greater than or equal to 3, so that the n distinct nth roots of z are the vertices of a regular n-gon or n-sided polygon. We set zeta equal to e raised to the power I times 2 pi over n. And so the nth root w equals v times zeta to the kth power. Zeta is in fact an nth root of 1, since by raising zeta to the nth power, we get zeta to the nth power equals 1. The viewer can also verify as an exercise that if zeta sub 1 and zeta sub 2 are nth roots of 1, then their product zeta sub 1 times zeta sub 2 and their quotient zeta sub 1 divided by zeta sub 2 are also nth roots of 1. Anyone familiar with number theory and modular arithmetic might also know that if m is a positive integer such that the greatest common divisor between m and n equals 1, or that m and n are relatively prime, then zeta to the nth power, or e raised to the power I times 2 pi times m over n, will generate all the nth roots of 1. What we mean by e raised to the power I times 2 pi times m over n generating all the nth roots of 1 is that the set e raised to the power I times 2 pi times m over n, e raised to the power I times 2 pi times m over n squared, etc., 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 all the way to e raised to the power I times 2 pi times m over n raised to the nth power, which is also equal to 1, is the set of all nth roots of 1. Because of the closure of the set of nth roots of 1 under multiplication and division, the set of nth roots of 1, to borrow a term from abstract algebra, is what is called a group under multiplication. Let's further examine the geometry of the nth roots of 1 with n greater than or equal to 3. The graph on screen shows the n-gon whose vertices are the nth roots of 1. 2 pi over n counterclockwise from the root 1 is the root zeta. The next root is zeta squared that by De Moivre's formula doubles the argument of zeta. The rest of the nth roots of 1 are also powers of zeta and continue to complete the vertices of the n-sided polygon. Each vertex being a complex number can also be regarded as a vector. After all, the set of complex numbers is a vector space under the operations of addition and scalar multiplication where the scalars are complex numbers. Let's take the vector associated with the root 1. To this vector, we add the vector zeta, and then zeta squared, etc., 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 and so on. The graph is indicating that the n distinct nth roots of 1 add up to 0. Let's prove this well-known result. One might recognize this sum, that if we multiply this by the quantity 1 minus zeta, the result is 1 minus zeta to the nth power. Zeta to the nth power is 1, since zeta is an nth root of 1. Therefore, 1 minus zeta to the nth power is 0. N is at least 3, so that e raised to the power I times 2 pi over n, or zeta, is not equal to 1. And 1 minus zeta is not equal to 0, so that we can divide by 1 minus zeta. Therefore, 1 plus zeta squared plus etc., 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 all the way to zeta to the n minus 1 power must be 0. We take the exercise a little further and show that the sum from k equals 0 to n minus 1 of cosine of 2 pi times k over n, and the sum from k equals 0 to n minus 1 of sine of 2 pi times k over n are both 0 for n greater than or equal to 3. Zeta, or e raised to the power I times 2 pi over n, is equal to cosine of 2 pi over n plus I times sine of 2 pi over n. De Moivre's formula says that for every non-negative integer k, the quantity cosine of 2 pi over n plus I times sine of 2 pi over n raised to the kth power equals cosine of 2 pi times k over n plus I times sine of 2 pi times k over n. And so, replacing each zeta to the kth power for k equals 0 to n minus 1 with the equivalent quantity, we get this equation. The real part of the left side is the sum of 1 and the cosines, and the imaginary part is the sum of the sines. This sum is equal to 0 if and only if its real part is 0 and its imaginary part is also 0. Therefore, in summation form, we have the sum from k equals 0 to n minus 1 of cosine of 2 pi times k over n equals 0, and the sum from k equals 0 to n minus 1 of this time sine of 2 pi times k over n equals 0. These equations hold also for n equals 2, which is an exercise that we leave for the viewer.